Welcome to the session on numerical methods, the Newton-Raphson method. The objectives for this session are to find approximations to the solutions of equations of the form f of x equals 0 using the Newton-Raphson method. To solve an equation of the form f of x equals 0 using the Newton-Raphson method, you need to be able to differentiate f of x. The Newton-Raphson formula is xn plus 1 equals xn minus f of xn divided by f dash of xn. Let's take a look at the idea behind the Newton-Raphson formula. Tangent lines are used to find increasingly accurate approximations of a root. The value of xn plus 1 is the point at which the tangent to the graph at xn, f of xn intersects the x-axis. So, for example, if we consider this graph and this sketch of y equals f of x, we begin with the point x0, as shown here. The coordinate is x0, f of x0. And the tangent line is as shown. The next point along is the value x1. This is the point at which this tangent intersects the x-axis. Next we consider the tangent to the point x1, f of x1, as shown here. And the next point along is x2. And then we consider the tangent at this point, x2, f of x2, and so on. As you can see, these points are gradually converging towards a root, or the point at which f of x equals 0. However, we do have to be careful when choosing x0. The Newton-Raphson method may converge to a root extremely slowly or not converge at all if the starting value x0 is not chosen with care. So, for example, in this graph, y equals f of x, the roots are here as shown. If we consider x0 as the point highlighted, and then consider the tangent at the point x0, f of x0, then notice that the tangent will never intersect the x-axis as it is parallel to it. So if x0 is at a turning point, the method will fail because f dash of x0 is equal to 0, and division by 0 in the formula is not possible. Let's now consider another scenario. We have the same graph and the same roots, but this time we take x0 at a point that is a little bit away from the turning point. When we consider the tangent at this point, then the next point along, x1, is much further away than from the root. So if x0 is near a turning point, or f dash of x0 is close to 0, then x0, f of x0 will intercept the x-axis a long way from x0. Now let's take a look at an example. Pause the video and have a go. Press play when you're ready to view the solutions. Let's take a look at part A first. We have that a function f of x is equal to x squared minus 3 over x squared, where x is greater than or equal to 0. we are required to show that a root of the equation f of x equals 0 lies in the interval 1.3, 1.5. So let's solve this. First consider the point x equals 1.3. If we plug this into our equation for f of x, we obtain f of 1.3 equals minus 0.085. Similarly, if we consider the point x equals 1.5 and plug this into our equation for f of x, we obtain f of 1.5 equals 0.916. Since there is a change of sign in the interval from minus to plus, we can conclude that there must be a root alpha in this interval. Now let's take a look at part B. We are considering the same function, and we're required to differentiate this to find f dash of x. So let's solve this. F of x is equal to x squared minus 3 over x squared, which can also be expressed as minus 3 times x to the minus 2. So if we differentiate this, we obtain f dash of x equals 2x. Here we've differentiated x squared, minus 3 times minus 2 times x to the minus 3. And here, of course, we've differentiated minus 3x to the minus 2. If we tidy up, we obtain that f dash of x is equal to 2x plus 6x to the power minus 3. Now let's take a look at part C. We are considering again the same function. By taking x naught equals 1.3, apply the Newton-Raphson process once to f of x to obtain a second approximation to the root alpha. Give your answer to 3 decimal places. So let's solve this. From the Newton-Raphson formula, we have that x1 equals x naught minus f of x naught divided by f dash of x naught. Here, of course, we have that n is equal to 0. We also have the starting value x naught equals 1.3. Now from part B, we have that f dash of x equals 2x plus 6x to the power minus 3. So we have that f dash of x naught equals 2 times 1.3 plus 6 times 1.3 to the power minus 3. And this is equal to 5.330997 and so on. We will now find the value of f of x naught when x naught equals 1.3. Because, of course, f of x naught is part of the formula. So plugging in x naught equals 1.3 into f of x gives us 1.3 squared minus 3 times 1.3 to the power minus 2, which is equal to minus 0.08515. Now we can apply this to our formula for x1, because this is equal to x naught minus f of x naught divided by f dash of x naught. So, plugging in all the values gives us that x1 equals 1.3 minus 0.08515 divided by 5.330997. To give us that x1 equals 1.316. This brings us to the end of this session. If you have understood its contents, you should be able to find approximations to the solutions of equations of the form f of x equals 0 using the Newton-Raphson method. Thank you very much for listening. To understand this topic in greater depth, do attempt the exercises in your textbook related to this topic.